Okay, our next talk is actually from one of our sponsoring organization, Fujitsu. Right, so it'll be Mr. Gary Evans. He's a senior manager of Fujitsu Australia Limited. And his topic today will be exploring the benefits of learned indexes in PostgreSQL, theory and implementation. It's a 25-minute talk. Right, so let's pass the mic over to him.
All right, thanks for that. So as mentioned, my name's Gary. I'm here from Fujitsu Australia, so I'm based in Brisbane. So you can hear me okay there? Is that all right? I'll try and hold the mic up there. So this is a talk I put together actually for Postgres Developer Conference in Montreal in May. A while ago, I was sort of looking at some of the new AI functionality in Postgres, like pgvector and PostgreSML, and sort of looking at some of the use cases that was being used for at the moment. And I came across some old university papers around learn indexes, which is sort of the concept of applying machine learning to augment or replace traditional indexes. And I thought, look, this is really interesting, and I dug into it a little bit more, and we decided to set up a little bit of a project and investigate this, and we thought this could be a really good new open source project to look into. So we decided, it'd be good to go and talk to some of the developers and discuss it there. So I put together a bit of a presentation, and we put it in, and it got accepted for the talk. So I thought, hey, this is a good opportunity to come around and raise awareness for the topic so more people know about it, drum up a bit of interest before heading across and talking to some of the developers and getting some feedback from. So this is a bit of a cut down version of the talk. I'm certainly not an expert, a data scientist, and I don't think I did that great at calculus at college either. So I'm not going to talk so much about the models, but our focus is really going to be about how can we take this concept and move it into PostgreSQL, and that's what the talk there is going to be about. Today I'm going to cover these areas, so I'll talk a little bit about the motivation for exploring alternative indexing approaches in PostgreSQL. Then we'll cover a little bit about the concept of learned indexes, how they work, with some simple examples on the slides. And then I'll sort of cover some of the studies that I came across and started researching. And then the bit that the presentation in May is about is really, how can this be integrated into PostgreSQL? So motivation, I guess indexes in PostgreSQL could arguably be said they're the most important performance optimization in the database. There's been a lot of investment in this area over many years now. We've got the index access method API, which is sort of an abstraction of indexes or a load of pointers for callback functions. So indexes can be continually improved and implemented independent to the core code. And there's been a lot of indexes that have been implemented over the years to handle different types of data. And then we've got the B-tree index. If we just look at that one alone, which is probably the primary index in PostgreSQL, there's been a lot of optimization in there. We've got the Lehman-Yau algorithm is probably the first layer of optimization. And then if we look a bit further, there's the B-tree plus to support concurrency and range stuff. And then there's a lot of independent PostgreSQL specific optimizations like heap-only tuples, B-tree deduplication. What else is there? Parallel index scans, covered indexes, and things like that. So why with all this effort that's gone in and refactoring over the years, we have a really good base for indexing, would we look at some alternate options? Sorry, I'll try and keep it a bit closer. Well, in the data landscape, things change very regularly. Data complexity and volumes change dramatically. If we look at IoT with sensors, we all know there's a heap more information coming into databases. And with that volume, B-trees or other indexes can struggle a little bit, and we see projects like Timescale DB that's come in to especially handle that type of data. And talking about the volume of data, as the data grows, obviously the size of the indexes grow as well. And if we look at a typical database now with a lot of indexing on it, it represents a very large portion of a database. So can we reduce that and make it more efficient? Also, I guess indexes and PostgreSQL are optimized for heavy read access. Write access can create some bottlenecks as that area, and then sharding as well, they can struggle a little bit as well. So there are some challenges there for our traditional indexes. Machine learning, which we're sort of looking at with learned indexes, there's been, the models have matured, there's been some big advances there. In hardware as well, we've seen a move to using GPUs for AI, and then we've seen Google bring out their tensor processing units, and now we've got AWS, Microsoft, Meta are all doing their own silicon at the moment with their own neural processing units as they set up AI infrastructure around the world. So it's certainly impacting things, and there's a lot going on there. And then, of course, it's databases. It's a competitive landscape. There's a lot of databases out there, and as members of the community for PostgreSQL, we're always looking at how we can improve it and make changes in there. There's also a big shift towards data-driven optimization. We see a lot of operators nowadays that have got a lot of data-driven optimizations to automatically scale out and scale back. I think last year at FOSSASIA I saw a DB Tune was here. They use machine learning to automatically tune databases as well. So maybe learned indexes and using machine learning to do that task is the next area that we might look at in this area. So that's, I guess, the motivation for looking in this area. I'll talk a little bit about the concept of applying machine learning to indexes. Some of the papers, I guess the core concept is to change thinking away from thinking of the data that we index as a black box and scaling it on volume. So if we look at the B-tree index, for example, as the data grows, we just add more branches and more nodes, and we scale up on volume. We did hear earlier there is some catalog information like histograms, how many nulls are in the data set, and some additional information there, but generally we just scale up based on volume. So the idea with machine learning is that we get a bit more insight into what the data looks like, the distribution patterns and like that. So this is an example out of an early paper, the first one I came across, a case for learned indexes. It was done by Stanford University and Google back in 2018. And this is pretty much where this diagram comes from. And they sort of say, well, what is a B-tree index? We have a key coming in to a piece of data, and then we get a starting position where we search through a range of data in our heap or our leaf nodes until we find the piece of data that we want. So if we abstract this idea, and I better do the click myself. If we abstract this idea and think of it in terms of a function, we could end up with something like this, where we replace the index with maybe a model at a very simplest level, maybe a linear function, which takes an x in and a y out, and maybe a model can predict the position of the piece of data we're looking for instead of going through that whole process. So that's sort of the concept, and then we have a error factor, and that's sort of how we can visualize going across to it. I think the battery must be low. So a very simple example that's given in a lot of, it doesn't come out very well there. A simple example given in some papers is if we've got a B-tree index here, and it has a key of that's a sequence of integers, say from 0 to 5 million or 10 million as the key. We can still use a B-tree index to find the piece of data that we want, but why navigate through our whole tree and then having to do the binary search in the leaf node to find the data we're after, when we can just use the key as a key or an index to the piece of data that we want. So that's a very simple example of what they're talking about. And it's just a case of understanding the data distribution and what that data looks like. So instead, we could replace that with a simple linear function where x is the key coming in, 110, and maybe y going out could be we can calculate the number of pages and an offset to get to the piece of data we want. So sounds reasonable, but yes, it's very simplistic and it's never quite that straightforward. But some of it, sorry, I got a really sore throat from earlier. So, but yeah, it's never that, data doesn't always look like that. Most of the data we look at in databases, a lot of it doesn't even conform to well-known distribution patterns that we know of. And there's a whole lot of other issues in terms of that using machine learning to do this that I've listed down on the right. But machine learning does help us abstract a little bit and understand what the data distribution looks like until we zoom in. So it's actually from these studies, it's a really effective way of narrowing down to a very small percentile, the last mile of whereabouts the data we're after could be located on disk. But yes, it's very challenging on that last part to find the piece of data we want. And if we zoom in on any distribution curve to see what the data looks like when it's following it, you'll find it gets much more grainy and the data doesn't quite fall on the lines that we're looking at. So I'll probably talk about implementation later, but as we know with the index access method API, we have a number of indexes that set up an initialization location. We have a handler registered against some of those index types. So we know when we create an index, a traditional index of type B tree, we know exactly which handler we're going to call and a bit of code that we're going to call when we say create index, or we want to do a scan, or we want to insert a value into the index. Learned indexes are going to be a bit different. We don't know what the model's going to look like. We don't know what the data's like. We've got to train that model first for it to be accurate, to get the error down to a small enough value that we're confident in it. So it's not like we can just create a learn index and register a function to handle that. So it's actually quite involved, and that's what our talk's going to be about in May. And we'll be covering some ideas and looking for some people to get involved in the project with us. So the paper I came across that sort of piqued my interest in this back in 2018 was the case for learned indexes, Stanford University and Google. I think it's the first paper or study that came out that really showed that learned indexes could work. They compared an internal B tree, an optimized B tree that was used internally at Google. And some of the early tests they did, I think the B tree, they tested on some realistic Google data sets, but they tested on 4 different types of indexes. So there was integers, timestamps, strings, and some geospatial data as well. But the first time they ran this, the B tree index ran about 200 nanoseconds to find a piece of data. And when they used TensorFlow to build their first models and run it there, it was about 80,000 nanoseconds to find this first piece of data. So it wasn't a very good result. They did a lot of work over a period of time, and they ended up creating, well, a few frameworks, but the key thing they created was the recursive index model. I should have put a diagram in a little bit to show it, but it's a multi-layered staged approach where each stage and the different layers was a multi-layer perception or perceptor neural network, and it was very, very small. And the idea is that it could use these neural networks to calculate for that piece of data. It would learn which was the next neural network that it should be using to then refine that down. It would refine it all the way down to till it gets close to the output layer, and then it would use something like a linear function to pick the particular value for it to come out. And when they sort of got this model working with a bit of time on these data sets, they were starting to find that they were performing very well, and they could actually outperform traditional indexes by 2 to 3 times. And the footprint's much smaller. Instead of having a big index sitting there in memory, it was a case of just storing the models and then running the input values or the keys through the models. The only thing about those early studies is single-dimensional data that they looked at. It didn't work very well. They didn't account for updates and things like that. And outliers weren't handled very well either. But some of the latest studies that have occurred, there's ALEX, an updatable adaptive learn index that Microsoft did, and that was an improved model. Same sort of principle, same sort of structure, with a multi-staged, multi-layer neural network, and that would handle that. And then later on, I think Google did one, I haven't got it up there, called LIP, which was a learned index, precision position or something index, that started, based on RIN, that started handling those outliers in a much more efficient way and maintaining accuracy. You can sort of see the velocity of papers increase as time goes. And you can see where the early focus was on just general model design and optimizing that model, right through to today, where we're sort of looking at integrating it into some existing technologies on realistic data. I'll probably point out, so some of the work we've done so far, we've decided what we should do first, as well as focusing on how can we put this into PostgreSQL, which I'll talk about shortly, is rerunning some of these old studies, but instead of using, use PostgreSQL's B-tree index instead of using Google's internal optimized one. We're still sort of using the approach of, we're using different data sets, and we're still using the approach of using TensorFlow and then compiling them into a C+ model and getting benchmarking off of those. Excuse me. So because this is in Canada, in Montreal, I had a bit of a look around to see if there's anything or groups doing anything locally, just out of interest. And I came across the Very Large Database, International Very Large Database Conference that was held in 2023 in Vancouver, which of course is very close to Montreal, I think. And I was surprised to find there was 11 papers accepted at a sort of highly academic conference around learned indexes. And this list excludes things where they're looking at using machine learning for other activities, like in the query planner and other parts of the database. So I thought that was really interesting, that in the academic world there is such a big interest in this area. So why PostgreSQL? Why do I want to start looking at implementing this into PostgreSQL? As we know, PostgreSQL is very extensible. We talked about the index access method API. So I say it's not straightforward to write an access method, but that's certainly a part of it. There's a growing ecosystem with PG vector and machine learning in that area. There's block range indexes and declarative partitioning, which aligns very well with some of the concepts in machine learning and AI as well. We know we have a very good concurrency control system, so that can help us in terms of making sure we're not blocking anything, less when we start managing and doing things with these learned indexes. It's got a very rich indexing framework, so the proposal we're looking at is we don't replace them. We continue using ordinary indexes, and we can learn from how those indexes are used to train and create more effective models. And of course, we've got a really active research group within the PostgreSQL community, and that's part of the idea of going along to the developer conference and talking to those experts over there about this and getting some feedback and drumming up a bit of interest. So, just a very high level, our general approach to this is add learned indexes as an optional setting, and keep traditional indexes in place so there's something to fall back on. I mentioned 3 models earlier on, so there's RIM, there's LIT, there's ALEX. There's also hybrid models as well. So you could have this staged, layered structure of neural networks, and then where the error wasn't low enough or sufficient enough, you could have a B-tree index in there, but that B-tree index, of course, was on a very small section of data by the time it reached that part of the structure. So it's not like you had a very big index. So that's an alternate model that's been investigated as well. So the idea is we deploy a traditional index, we let it run for a while, typically in a lower environment before going to production, even though the data's not going to be that realistic. But we we sort of analyze it and say, is a learned index going to be beneficial in this situation? Because it's not in all situations, as we know, everything's different. And once we determine that it is, then we do a more detailed extraction of the data, which I'll talk about in a minute, around it. And that would allow us to build an appropriate model to start with and train that model. And then once we've done that, we can look at, well, how do we deploy it then alongside the old index? And of course, data distributions, patterns change over time as we add data to them. So we can't just leave the model there because the error might grow over time. So we might have to retrain it or do something there. So it's going to be a very stepped approach, I guess, to implement something like this. Doing the learning is obviously at this point in time not something you want to do in PostgreSQL while you're running it and you've got users accessing it. It's very intensive and can take a lot of time to train models. But you know, the way these neural processing units are going and the amount of hardware, you know, the rate it's being developed and rolled out, who knows, maybe one day in the future down the track, there's an opportunity to train models real time in the database when that hardware's there. But at the moment, we'll need an external service that we take sample data out to train it, establish our model, and then we can move it back into the running database. It's getting a bit short in time. So we can sort of break that. At the moment, our approach is to break it down into 4 different steps. Determine if the learned index is potentially beneficial, train the model externally, deploy the index, sort of measure it against the traditional index, use it as a failback, monitor it, and then we've got a strategy for how do we update that model over a period of time as it loses its effectiveness, if it does. Some of the testing we've done so far has been pretty comparable to some of those earlier things. So what we haven't realized or we don't understand is if, you know, Postgres's B tree is more efficient than the one Google used or not. But we do know when we use TensorFlow now, the hardware that's available to the model is a lot faster than what it used to be back then in terms of the time it takes to train the model. In terms of running the model in inference, of course, that doesn't take much time anyway. But in terms of the quality of the model, we're not really sure how what we've got now compares to what we had back then. I've just sort of put some ideas in against each of those stages there to give a bit of an indication of some of the things we do. I'm very aware this is just a 25-minute session. So I'll probably let you have a look at some of the details in these slides, and you can send me an email or something if you've got any questions later on, or maybe you'd like to be involved. But there's a whole lot of information that we can access to give us an insight into not just the data distribution, but how it's used. So row counts, cardinality, the query level features, whether it's range-based or equality-based for most of the queries, or maybe it's mainly used in joins, will give us an access pattern. So there's a whole lot of information. Even the existing indexes that are used, or the type of index, will give us a reasonable amount of information that helps us determine what type of model should be used. I won't cover some of these. I sort of talked about what the model looked like, but there's been a lot of experimentations with all different types, model types in this area. And then I'll just finish off on the large page. There is a whole heap of challenges that we've identified so far, and I'm sure once we start talking to some of the developers, and maybe you guys here, there's going to be a whole lot more challenges that we haven't really thought of. So it's sort of early days at the moment, but you know, in terms of that multi-stage approach, how are we going to manage the models? We sort of got a reasonable idea of how to integrate into the index access method API, but we're going to need some sort of integration directly into the query planner and optimizer. You know, just for example, one of the challenges might be how do we estimate for planning how long an index is going to take and things like that. It's a bit more challenging with learned indexes because you don't have the information available to that you do with a more traditional one. Concurrency and transaction safety isn't something we've looked at in a big way so far, so that's going to be another challenge. vacuuming in it. So there's a lot of challenges there we're looking at, and hopefully between now and May we'll understand a bit more, but hopefully in May we'll be able to talk to some experts in some of these different areas and come away with a lot more information to help with this. And the plan is sort of after that, maybe June, we'll make some of what we've got available in a repository, GitHub somewhere, and try and build a little bit of a project around it. So I just thought today would be it'd be nice just to cover something different and new rather than talking about an existing feature in the product. It just gives you an idea of a new area that we decided let's have a look at, and we're sort of embracing that open source approach of bringing up an idea to a community and starting off a new project. So I'll finish there. I do have a drone to give away. Last time I gave a gift away in, I think, Singapore a few years ago, I did it randomly and drew a number out of the hatch. And the guy who won it was the only guy who was snoring in my session. He'd fallen asleep. So I've decided I'm not going to do a random one again. Someone's got to show that they're paying attention. I won't make it as hard as Nishke did this morning with his session. So it'll be a quick fire of hands as to who gets it. So earlier on, I mentioned a study in 2018 with Google. Who was the university involved? Hands up. Yeah, there you go, mate. This is well done. Yeah, thanks. Thank you. All right. I'm happy to answer any questions anyone's got or any feedback.
Any questions for Mr. Gary?
Yeah.
Oh yeah, I'm curious about when you said like training the model, like what exactly does it train to do? Does it try to predict which part of the database gets access and index only those, or does it like try to do something else?
So what it does an overfit. It takes a data set that you've got that you want to index, and it will generally, when you train a neural network, you'll say, well, we'll use 80% for training and 20% of that data for testing. And so it will just run through all that data through the model, and it'll test the error at the end, and it will just weights in each of those neural networks. So, for example, at key X or key 5, it might decide that portion of the data distribution it's more accurate using a neural network model down this side of the tree, whereas up the other end of the data distribution, it's more accurate navigating down this side of neural networks, and it's better handled by a neural network over in this part there. And so the idea is the first one sort of says, for that key, you're in this chunk of data rather than this chunk, and so I'm going to send you down to this neural network here, and from that data, it's going to say, well, if you're in this part, I'll send you over here, and if you're in this part, I'll send you there, because it can do the check. Until you get down, and that's where it gets very difficult with I was talking about last mile, that last part, and that's where rather than using a neural network, it'll use something like a linear regression function or a polynomial regression function to come back with a single value. And results are showing, there's odd, weird results, and there's ways of handling that. But the results have been pretty positive, and as I say, where you get a part of the distribution that's not very accurate, maybe something weird happened in the business at that point in time, you can always revert to a smaller B-tree index at that part of the bottom of the model, whether it's RMI or ALEX.
I'm curious, what was the input to the B-tree?
The keys, so you just take a random number of keys and you run it multiple times. So if you're testing for equality and you've got 200 million records, you probably don't want to use the B tree 200 million times or whatever, but you take a range of data, and the benchmarking's not done so much against the testing, because that's just to establish the model. It's at inference, and so when you're doing it at inference, you might say, let's just test 100 or 150 random keys, and you do 150 times against a B tree, and then you do the same thing against the model that's fitted, or fitted just means trained, that you've trained. Does that answer the question, Sora?
Yeah, thanks. So it okay.
Okay, so we are out of time for Q&A. So please engage Mr. Gary after this.
Yep. Yeah. All right, well, thanks everyone.
Okay, thank you.
Sorry about the mic, hopefully you can still hear me.